Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to resistance, inductance, capacitance and resistive, inductive, capacitive circuits. So far we have discussed them separately and their combination with resistance, that is purely resistive, purely inductive, purely capacitive, and RL and RC circuit. In this video we are going to discuss about RLC circuit, some basic concepts. So here we have is a series RLC circuit where we have the three circuit elements: resistance, inductance, capacitance, connected across a alternating voltage source. So here the net impedance, the net impedance of the circuit plays a very important role in deciding how this whole circuit will behave. Now before that, just a quick review. We remember RL circuit, where the net impedance is R plus j omega L, and here the current lags behind the voltage by an angle phi which is in between 0 and 90 degree. That we are clear. This is the voltage triangle and this is the impedance triangle impedance triangle. And then we have RC circuit, resistor and capacitor with impedance R minus j omega C, and here the current leads the voltage by an angle phi which is somewhere in between 0 and 90 degree, this being the voltage and this being the impedance triangle. So now for this RLC circuit, the net impedance plays a very important role. So here for an RLC circuit, the net impedance is equal to R plus J XL minus XC, where XL is equal to omega L, XC is equal to 1 by omega C. The inductor and capacitor, they are frequency dependent elements. So here whether XL, the inductive reactance, is greater than the capacitive reactance or the capacitive reactance is greater than the inductive reactance, that decides the overall behavior of the RLC circuit. Which parameter dominates? The reactance parameter. If the inductive reactance is greater than the capacitive reactance, then the circuit will behave more, it will be, it will tilt towards the RL side. It will overall behave like a RL circuit if the inductive reactance is greater than the capacitive reactance. Now if the capacitive reactance is greater than the inductive reactance, then the circuit, the RLC circuit, will behave like a RC circuit because of the dominance of capacitive reactance. This is the important thing, because if XL will be greater than XC, then we can disregard this capacitive reactance and simply write R plus JXL. Like suppose XL is equal to 100 ohm and XC is equal to somewhere like 10 ohm or something like that, then we can say that this thing, the inductive reactance, will play a huge role and the circuit is mainly, it will behave in an inductive manner, RL manner. If the whole thing is reversed, that is XC is equal to 100 ohm, here just I am giving an example, and XL is equal to 10 ohm, then we can disregard this inductive reactance and consider only the capacitor. the net capacitance in both the cases, here it will be J plus J90 ohm, here it will be minus J90 ohm. Here it will be capacitive, here it will be inductive. The behavior will be capacitive, here the behavior will be inductive. So, if we try to analyze it, for a RLC series circuit with net impedance this much, if the inductive reactance is greater than the capacitive reactance, then the overall circuit behavior will be inductive. It will be more like a RL circuit. So here we have the voltage drops across the resistor, inductor, capacitor. This is the impedance. If we try to represent it in phasor form, first we have taken again the current, the virtual value or RMS value as the reference. The voltage drop across the resistor, that is in phase with the current, okay. Then we have the voltage drop across the inductor, which leads the current by 90 degree, and as you can see from the arrowhead, it is of high magnitude, because as XL is greater than XC, so the voltage drop across the inductor will also be greater than the voltage drop across the capacitor, because voltage drop across the inductor is equal to I into XL, and voltage drop across the capacitor is I to XC. This is in the negative direction. So if XL is greater than XC, then obviously VL will be greater than VC. As you can see from this phasor diagram, the VL is from here to here. It is greater than VC, which is of smaller magnitude in the opposite direction. Here this arrowhead VL minus VC, that represents the difference between these two phases, that is VL and VC up to this. So the net resultant EMF, which is the applied EMF here, the virtual value, that is done by joining these 2 points. And again you can see here the phase angle between the applied EMF and the current, that is positive, and here this net EMF, it leads the current by an angle phi, which is somewhere in between 0 and 90 degree, which is the behavior of an inductive circuit, okay, which is the behavior of an inductive circuit, okay. Then we have a RLC circuit where XC is greater than XL, okay. So for this is the voltage triangle, and here this is the impedance triangle, okay. This is the impedance triangle, this is the voltage triangle, this is the impedance triangle. If we divide it by all the other parameters that are present, if we divide it by the current, we will get the impedance triangle. And this is XL minus XC, which is the difference between the inductive and capacitive reactance. XL, which is of high value, the inductive reactance. XC, which is of smaller magnitude in the opposite direction, capacitive reactance. And this is the resistance, which is which we get by dividing VR by IV, and this is the impedance Z, which we get by dividing EV by IV, okay. This is the impedance triangle for this condition. Now the other condition where capacitive reactance is greater than the inductive reactance. So in this case, the circuit, this RLC series circuit, will behave more like a RC circuit, because capacitive reactance is greater than the inductive reactance. As capacitive reactance is greater than the inductive reactance, so the voltage drop across the capacitor, which is represented by this arrowhead in the downward direction, vertically downward direction, VC, that will be more. The voltage drop across the inductor, it will be of smaller magnitude, as it is denoted here in the upward smaller arrow, and the difference between these voltage drops, two voltage drops, that is represented by VC minus VL, this up to this arrowhead. And Again, we have taken current as the reference, voltage drop across the resistor, that is in phase. VL leads the current by 90 degree, VC lags the current by 90 degree in clockwise direction, this is in anti-clockwise direction. So we get the net EMF, the resultant applied voltage, as joining this point and this point, the difference between the two voltage drops. This is the voltage triangle, and as you can see, the phase angle between the net resultant voltage and the current, that is in between 0 and 90 degree in the clockwise direction, and the current, it leads the voltage by this much angle. So this is the behavior of a RC circuit, where current leads the voltage by some angle which is in between 0 and 90 degree. So this is the voltage triangle, and if we divide every parameter by the current, we will get the impedance triangle. So this is resistance, which is got by VR by IV. We have the impedance, which we get by EV by IV. We have the capacitive reactance, which we get by VC by IV, inductive reactance XL, which we get by VL by IV, and XC minus XL, which we get by VC minus VL by IV. Okay, voltage triangle, impedance triangle. Now some important formulas associated with this. No matter what the situation, these formulas are applicable. The net voltage, be it the capacitive reactance dominant case or the inductive reactance dominant case, that will always be this voltage drop across the resistor, square of that, plus the difference between the voltage drop of across the inductor and capacitor, VL minus VC or VC minus VL, it doesn't matter because we are squaring it. So be it whatever value you get, whether it is positive or negative, when we square it, we will get the same result. So VR square plus VL minus VC whole square root over, that is the net voltage. Then the net impedance, that is equal to root over of R square plus XL minus XC whole square, which is equal to the ratio between the net EMF and the circuit current, EV by IB. We are taking the RMS values or virtual values here. Then we have the power factor or the cos of the angle between the voltage and current, that will be equal to R by Z. Okay, you can also take it in this way. If we consider the voltage triangle, here we are considering the impedance triangle, R by Z. If we consider the voltage triangle, it will be VR by EV in both the cases, VR by EV, but it's the same thing, because when we divide, okay, see, cos phi is equal to R by Z if we take the impedance triangle into consideration. Okay, impedance triangle. But if we take the voltage triangle, it will be VR by EV. If we divide IV and IV in both the cases, we will get same, R by Z. Okay, so same thing, it essentially means the same thing. So these are some of the important formulas. So the important thing to take from this discussion is that the behavior of RLC circuit, here we are taking the series circuit, it largely depends on the magnitude or the parameters, the frequency dependent parameters. Okay, the frequency of the supply, okay, this, and the values of inductance, how much Henry, how much Farad, that, and as a result of it, the inductive reactance and the capacitive reactance. Which one is greater than the other, that decides how the whole circuit will behave. If inductive reactance is greater than capacitive reactance, it will be RL. If capacitive reactance is greater than the inductive reactance, it will be RC. Okay, this is the simple thing.